Well, so okay, so we were discussing about this Vigo notation or order of GN in general, Vigo of GN, right? And we have seen several different examples. One example is this checking for duplicates in an array, okay? Whether uh, an integer t is containing in both the array A and B. That example also we have seen. And also there is one integer t, we are searching for one array A. Okay, so these are some of the examples we have seen, and based on that we have reached to one conclusion that whenever we are having for loops, that is the target point of analyzing algorithms. Okay, and bulk of the processing will be done based on that for loop. And also we have to fix up one philosophy, that means one idea based which will be taking bulk of the amount. Say for example here this is, that means how many times we are comparing. Okay? How many times we are comparing, actually we are comparing, and then that will be leading to the searching. So the comparing process, whether that comparing process how many times we are comparing, that is the main salient point here for analyzing. And now next notation that we will be checking is this omega notation. This omega notation, so this is called big omega, right? Big omega notation. And the previous one, this one was the big O. Okay? Big O notation. And now we are having this big omega notation. Okay, and before going into that, all the four different problems that we have discussed, for which you should be writing a code. Okay, you should be writing a code, and also you should be drawing some graph. Okay, based on, say you are working on say 5,000 input, and you are searching 5,000 different elements there in the array A, and you are searching one of the element in that, and say how many comparisons will be necessary for that. And if I am having say 1,000 elements, how many comparisons will be necessary? If I am having say 2,000 elements, then how many comparisons will be necessary? And then say here several different values I'll be getting, maybe something like this. Okay, so you plot a graph in this, the n inputs, number of inputs here, and in this how many comparisons will be necessary. So in this axis, y-axis, and the x-axis will be having this number of inputs we are having, and this you have to write, you have to plot these graphs in GNU plot. I'll be recommending everybody to switch to this Linux platform. Linux, preferably this Ubuntu. So you have to do this for these four problems that we have discussed in terms of this BIGO. And another thing you have to do is the GNU plot you are having and these BIGO notations and based on that examples I have given. So based on that, you have to prepare 2 pages document. 2 pages document. Yes, 2 pages document, and that document you have to prepare in LaTeX. Okay, in LaTeX you have to document. Okay, let me check again whether I am recording or not. Yes, I guess I am recording. Yes, I am recording. I'm recording. Okay, so 2 pages document you have to prepare, and that you have to prepare in LaTeX. Okay, so how can you learn LaTeX? Just Google it and see 2-3 videos, 5 minutes videos, and you can learn LaTeX. So it's not a big deal, and even if you are having problem, you can consult me. And there is one source, LaTeX wiki, that is a very good source, LaTeX wiki book for LaTeX. You can go through it. Okay, for further reference, LaTeX, how to do it. 2 pages document on BIGO. All 4 programs you have to write, and this graph also you have to plot in those 2 pages, and you have to submit. So I'll be giving you some kind of this as an assignment in the Moodle, but Moodle is I have created, but I haven't shared the link because it will be coming under this event semester, and then event semester they are creating. Okay, those who are looking after this Moodle. So once that will be created, I'll be sharing. So maybe within the next week. Yes, definitely. All lectures, all slides, all references I'll be giving. Okay, and your job is to study those, and I think many of you will not be doing any kind of studies. Do you study? Are you listening? How many of you have gone? How many uh, how many of you uh, thinking that you will be keeping it pending till the end of the semester? I think most 80% of the students thinking, okay, before 10 days it will be okay, right? So I think for algorithms I'll be suggesting that you should not be doing that. Okay, I think a huge amount of syllabus will be covered here. You got to do some work. Okay, we'll be posting assignments here to solve. You have to give it to us. Okay, and also there will be huge amount of syllabus to be covered, so many topics, so day-to-day study might be better anyway. Okay, so that was something you have to do in the next subsequent classes for the assignments. So you can think of this is the first assignment I have discussed. Before giving it to the Moodle, you start preparing it. Okay, so that whenever I'll be posting it to the Moodle, immediately you can submit. Okay, so next I'll be going to this omega notation. Okay, and this omega notation, so first this fn equal to say 2n plus 3, say from some algorithm that this has come. Okay, for some algorithms, and in the last class we have seen that maybe we have written this fn less equal to c of gn, maybe 3 of n. So this is our gn, this is our gn, and this is our C. So Fn equal to this 2n plus 3, that we have seen in the last class. So Fn less equal to C of Gn. Now this first of all I take the example and then we can go to this definition. Go to this definition. So 2n plus 3, I can also write that this is greater equals to 2n. 2n plus 3 greater equals to 2n. Okay. So this for some n naught, n greater equals to n naught, it will be true. And say if I am putting n equal to 0, so this thing is coming 3 and this thing is coming 0. Okay. So 3 greater than 0, so this is getting satisfied. So I guess for here this is our C2 and n naught here, this is our Gn, this is our Gn, and this is n naught here will be equals to 0. So that definition, and if Fn greater equals to some C times Gn, then we call that this is Fn equal to omega of Gn. Okay. So this, in the last class we have seen that okay, this Fn equal to order of n, and here this Fn equal to omega of n we will be writing. From here we will be writing omega n. So you see that definition is given here. So this is omega of Gn. Omega of Gn equal to a set of function Fn. So 2n plus 3 also will be greater equals to 2n. 2n plus 4 also will be greater equals to 2n, and all these things will be boiling down to this Fn equal to an plus b will be boiling down to this omega n also. So this is a set of function. Depending on a and b, we can have set of functions which will be classified as order of this omega of n. Okay. So this omega of n, that is equal to a set of function Fn, set of function Fn. So omega of n, this omega of Gn, omega of Gn, that will be equal to a set of function this Fn, such that this condition getting satisfied, 0 less equal to Cgn less equal to Fn. So here we have seen that Fn greater equals to Cgn, that means Cgn less equal to Fn. So Cgn less equal to Fn. So that is the condition to be satisfied, Cgn less equal to Fn, or Fn greater equals to Cgn, and that for some positive constant C, and for n greater equals to n greater equals to n naught. Okay, so this is the definition for omega. So for all n greater equals to n naught. The similar definition of this BIGO, but here the main thing is that in the BIGO it was that Fn less equal to C of Gn, but here this C Fn greater equals to this C of Gn. Okay. So this is the definition, and okay, we have seen the example as well how to do this. And say this another example, if we can take Fn equal to say 5n minus 5, so I can write that this is greater equals to 4n, I can write. Okay, so this, if n equals to 0, this is becoming minus 5, greater equals to 0, not satisfied. So n equals to say 1, 5 minus 5, it's 0, and it's great. This is 4 times 1, 4, not satisfying. So n equals to 2, So this is 10 minus 5. So this is 5 greater equals to 8, still not getting satisfied. N equals to 3. So this is 15 minus 5, that is 10, greater equals to 12, not satisfying. N equals to 4. So this is 16 and this is also 16. And n equals to 5. This is 20 and this is 20. N equals to this 6. So this is 25 and this is 24. Right. So I guess this this is n equals to 4. That means this was 15 and 16, not satisfying. This, from this onwards, it is getting satisfied. So our n naught will be equals to 5 here, right? And this is our C and this is our Gn, right? So this then now we can say that Fn is greater or equals to some Cgn, and we can say that this Fn equal to omega of Gn. Gn is n here, so omega n. So this is how we develop this omega n notation. Okay. So this is the solution. If somebody is telling that Fn equal to omega n, okay, then definitely you can check that whether he is telling right or wrong. Okay. Okay. So this is the case, and you see why this notation is important. Omega notation is why this is important. Why another notation? And this is convenient for computer science because say I am telling that every algorithm will be taking every algorithm of sorting, comparison based sorting, every comparison based sorting will be taking omega n log n time. The implication of this is that no matter how you are trying, but in general sense, the comparison based sorting, you cannot have it or the comparison based sorting will be taking greater or equals to n log n time. Okay, so that is the implication of this. It should be greater than, okay, n log n. So this greater equals to n log n. So that will be the implication whenever we are having this. So no matter how you are trying, we will be having. So it is a very convenient notation for saying some kind of lower bound. Okay. So this Fn greater equals to Cgn, mind you here. So that means if Cgn, say I am taking 10, that means Fn greater equals to 10. That means Fn is 10 or more. That means that is the lower bound. Okay. So the sorting algorithm, the lower bound is n log n. Right. So that means n log n time will be taking in general sense, in general input. Okay. So that's why this omega notation is very handy whenever we talk in terms of lower bound of some algorithm. Okay. So this lower bound, this is, so lower bound is coming from this notation, this greater equals to sign. Okay. So we have got this omega notation. So far what we have got this big O notation. Big O notation we have got omega notation, and we know when we should be using all these notations. Okay, with examples we have seen. And now the next notation that we will be trying to discuss is this theta notation. Okay, so again this the today's lecture is based on this CLRS. Okay, CLRS. This is from the CLRS book. Okay, so if you are trying to trying to consult CLRS book, this will be really handy. Okay. So now this you see by this definition omega, you see whenever I am having say this expression from some algorithms, fn equal to 2n plus 3, right? So now if somebody is telling okay it is less equal to 3n, then we have seen okay it's true, it's true. If somebody is telling, if some of you are telling, arguing the fact that okay sir this 2n plus 3 by definition also we can write that this is less equal to say 4n square, 4n square we can because if it is 2n plus 3 is, if it is less equal to 3n, then definitely it will be less equal to 4n square for some values of n, for some values of n naught, n greater equals to n naught. So that that is also true by definition. Okay. So if somebody is getting this and equating with this less equal to 4n square, that is also true. If somebody is telling okay it is 5n cube, that is also true. Okay. And if fn equal to 2n plus 3, if somebody is telling by having this condition getting satisfied with n square, and somebody is telling that fn equal to order of n square, that is also true. Okay, that is also true by definition of big O notation. But if somebody is giving that okay by seeing 2n plus 3, if somebody is giving order of n, that is much more tight, that is much more tight and much more efficient. But no one can say that if somebody is writing fn equal to order of n square, that is also right. So this this is if say this fn equal to 3n cube plus 3, 3n cube plus 3. And if somebody is telling okay this is greater equals to some constant k, that is also true. If somebody is telling this is greater equals to some 2n, that is also true. This is somebody is telling it is greater equals to some say 2n square, that is also true, right? And this is this by following this notation, say this n square, you can say there's 3n cube, this guys is omega n, we can say omega n square, we can say, right? Both will be going by the definition. And order of 1 also, this omega of this this omega 1 also, that means constant, it is greater than this constant, that is also true. So now this theta notation is an elegant way to solve this problem. Okay, the theta notation will be giving definitely will be giving the tight bound. So that's why we use this tight bound, and this theta notation is now a very popular notation among these computer scientists. So this you must be knowing. Okay, so let us take so this what this definition is telling. Okay, so first we take the example and then we'll be going to the definition. So at that time it will be much more clear to you. Okay, the definition. So first of all, take this our say favorite example 2n plus 3. Okay, so now you see this will be having this condition getting satisfied, fn less equal to c2 times gn. Okay, so I am writing that this is less equal to 3n, this is less equal to 3n. So some c here this will be c2 and this is our gn. And also this at that time, if we have seen that for some n naught greater equals to n naught, it is getting satisfied, n greater equals to n naught. We have already seen, right? So this fn equal to this condition getting satisfied, fn less equal to C2 of Gn. And also another thing is that this fn, so this condition also to be satisfied, this portion Cgn less equal to fn, C1 Gn less equal to fn. That means fn greater equals to C1 times Gn. Okay, so this fn, so this, what is fn here? So this fn is 2n plus 3, and I can write that this is greater equals to 2n. Okay, and we have seen maybe n greater equals to 0, it is getting satisfied, and it is this C1 is 2, and this is our Gn. Okay, so look at this implication. Okay, so here also this Gn is there, and here also this Gn. Okay, here also this Gn. So this Gn is n, the same. So this Gn is n here, Gn is n here. Okay, so both the cases the same Gn we are using. So that is, there lies the catch. Okay, there lies the catch. If somebody is telling fn less equal to 3 times n square, 3 times n square, if somebody is telling, right, then that will not be satisfying this condition. This Gn will be here n, and Gn will be here n square. So both will not be same. So we cannot say that is Gn. We might be telling that is some kind of, say, Hn. Okay, something like that. So this Gn, that means both the cases it will be same. If this is the case, then we are having this condition getting satisfied, right? So you cannot say fn less equal to 3n square, and somebody is writing here fn greater equals to 2n. So you cannot do this in theta notation. So this theta of Gn is also a set of function fn. There exists positive constants C1 and C2 and n naught such that this condition will be satisfied. Here we are satisfying both this condition. Okay, for all n greater equals to n naught. So for all n greater equals to n naught, this will be getting satisfied. So which n naught I will be taking? Say here the n naught is, say, 0. Say I don't know, I am not remembering what is the n naught here. Maybe 3 or something like that. Okay, so now whichever is the maximum, so maximum, so this maximum of this 3 and 0, maximum of this 3 and 0, I have to take 3. So n naught value will be equal to that. Okay, so here in our example, maybe this n naught value might be 3. Okay, so this is the theta notation. Okay, and here then I'll be telling that fn, if both the condition getting satisfied, both the condition, then I'll be telling fn is equal to theta of Gn. Theta of Gn, here Gn is n, so theta of n. So whenever somebody will be telling that fn equal to theta n, then both the upper bound and lower bound is in tight fashion. Okay, so that's why this theta notation, if somebody is giving, then you can rely on that. Okay, so if he or she has done in a confident way, if he or she has learned it to do that, then definitely you can rely. Okay, that notation is very, very good, right? So this is the theta notation, and there are two more notations we are having. So one is this little o notation, little o. So this is little o notation. So little o notation. We have seen big O, we have seen big O, right? Now we are seeing little o, okay? Little o. So this big O we have done, and now we have to do this little o, right? Okay, so this little o is again this same thing, order of small o of gn, small o of gn equal to a set of function fn, and such that this condition getting satisfied for positive constant c greater than 0, there exists a constant n0 greater equals to 0, such that n0 greater than 0, there exists n0 greater than 0, such that this condition getting satisfied, fn is strictly less than cgn. So in the big O notation we have got fn less equal to c times gn, and here what we are giving is fn less equal to, strictly less equal to cgn. So here one example is given that this 2n, say fn equals to this 2n. Example. Fn equals to 2n, right? And that I am telling that it is strictly less than maybe this c times maybe 1 times or say 2 times n square. Okay, it is strictly less than. For definitely some n not greater than 0, it will be satisfying. So you take the value n equal to 0. Say we can start, say n equals to 1 here, say 2, and here 2. Okay. N equals to 2 here, so it is 4, and it might be 8. Okay, so it is in not greater than greater than this 2. So n not this greater equals to 2, we are getting this satisfied. Okay. So fn is strictly less than this 2 times n square. Okay, so that in that whenever this condition getting satisfied, then we are telling that this fn is small o of gn, that is n square. This is our gn. This is our gn, small o of n square, right? So there is another alternative definition for this, which is given here. Okay, which is given here, that is taking the help of this limit. So this limit n tends to infinity. So this n tends to infinity, this fn by gn, that will be equals to 0. So this, in our previous example, this fn is 2n, and this gn was n square. Okay, so you see, if I am putting the value, say n equals to say 10, okay, n equals to 10. So in that case, fn will be 2 times 10, that is 20, and this gn will be 10 times 10, that is 100. So 20 by 100 it will be having. So as you see this, whenever this n will be larger and larger, at that time this fn by gn will be going to 0, okay, tending to 0, right? So this alternative definition is also a valid one. Okay, this is much more I think as far as visualization is concerned, this is much more easier to visualize. Okay, so limit n tends to infinity fn by gn, that is equal to 0, right, when n is growing larger and larger. Okay, so n tends to infinity. Whenever we talk about the algorithms analysis, we talk about larger and larger values of n, right? So this is the little o notation. One more notation is left, omega little omega notation, that we'll be doing in the next class, right? And then we'll be going to this divide and conquer chapter. Okay, so if you have any question right now, you can ask me. Stop presenting right now.